So in this first video of the lecture, we're going to take a look at a historical perspective of computing. And for those of you that have taken the intro course with me, either this semester or last semester, this is a module that we do within the intro course as well. So if it looks familiar, that's something you have seen before. Really, the way that we're going to go into more detail is in the example problem video that I do in the next module. So why are we talking about computing in an intro to kind of engineering programming course? Well, as we talked about in lecture 0, what really programming is about is kind of automating certain workflows or tasks within a computer. And when we think about what a computer is as a piece of hardware, it's just going to be a device that's optimized or designed in order to do the operation of computation. And really, computation at the end of the day is all about doing math. So really, when we think about what a computer is doing, whether it's kind of an actual engineering productivity application, maybe finite element analysis, where we're analyzing the capacity of a structure to maintain a certain load, naturally, that's going to be math. But even if it's the generation of actual graphics or kind of routing information along the internet, those operations fundamentally are all broken down, as we'll see a little bit later, into the same fundamental set of underlying capacity of a computer to do mathematics. So really the idea of kind of trying to automate math using hardware is something that dates back a very long way in the timeline of human history, as you see here. However, we're going to focus on a particular subset of machines that kind of dominate the architecture that we see today in the resources that we have available, which are actually called a digital computer. So when we think about a digital computer, a couple things that I want you to be aware of. First and foremost, it stores information in a discrete form, particularly using a binary number system. Now, when you talk about a binary number system, in contrast to the number system that we use every day, it's only going to have 2 digits, and each of the place values is going to be a factor of 2 versus a factor of 10. And for those of you that are going down the electrical and computer engineering route, you'll see why the binary number system is so valuable from the perspective of really providing a certain level of noise immunity when you either store or transmit a bunch of ones and zeros. If you only have 2 levels or 2 decisions that you have to make the decision or differentiate between, it's a lot easier than maybe if you're trying to store or transmit 4 or 5 levels. So a lot of times people don't get that really the utility of storing information in 2 states, either ones or zeros, is really about providing noise immunity, because unfortunately when you store information or send it over a distance, it's always going to be corrupted by noise. So in addition to storing information in that discrete form, digital computers are also differentiated by the fact that they're really not that smart. They only know how to do a basic set of things, and those things are known as their instruction set. So when you look at any computing device, and we'll talk about what kind of classifies a computing device a little bit later, really the differentiation across those fundamental microcontrollers or microprocessors is their instruction set architecture. So when you think about the 2 kind of aspects that I want you to know about a digital computer, they store information in binary, and they only can do a very simplistic set of operations called an instruction set, but those instruction sets can be programmed in order to do anything sophisticated that you would actually want to do. So the third bullet there, or kind of the final bullet, under the key ideals point, is what actually makes something a computer. Well, there's lots of different definitions here, but usually if you refer to the idea of a von Neumann architecture, or having a computer that's actually Turing complete, and we'll talk about Alan Turing a little bit later on in the course, really you're talking about something that has the capability to store information in what's known as scratch memory. And this is a kind of memory that's trying to help the actual computations be made. It's not something that you're interested in storing long-term. It's just kind of a scratch paper that you're keeping around while you're making a computation. And in a modern computer, that is called random access memory, or RAM. So that's what we mean by the memory within the von Neumann architecture of a computer. In addition, for a computer to be useful, you have to have the capability to get information in and take it out. On what we're familiar with modern desktop computing, those can be things like mice, the actual mouse that you use, or a keyboard. In a modern HMD, it could be something more sophisticated, like maybe an eye tracking input or some sort of front-facing camera that is kind of tracking your touch to interact with the hologram. In addition to being able to get information in, take it out, and store information for short-term in computation, you also have to have the capability to have a processing unit to actually do the underlying math that you're trying to do. So those are the 3 key parts of a digital computer. So let's talk a little bit about binary encoding. And we're going to look at this in a lot more detail in the example problems that I do in the next module. But the key thing that I want you to know is when you talk about a number in base 10, like say something like 727, the actual interpretation of this number comes from two things. It comes from the fact that you have digits, and those digits are arranged in such a manner that they have some meaning of what's known as a place value. So we say that this 7 is in the ones place, this 2 is in the tens place, and this 7 is in the hundreds place. And if you actually expand out that number, think about when you first learned about what numbers mean. You can write this 7 in the hundreds place, or 700, as 7 times 100. And you can write this 2 in the tens place as 2 times 10. And this 7 in the ones place is 7 times 1. Now, why would you ever want to do that? Well, when you write it in this form, you start to see how both the digit and the place value contribute to the underlying meaning of that encoding of the number. Particularly this 100, 10, and 1, they can all be written as 10 raised to a power. Why 10? Because 10 is the actual base of the decimal number system. The digits 7, 2, and 7, what's special about them? Well, the special thing is that any valid digit that would be in there has to be one out of a set of 10. And the set of 10 valid digits, of course, are going to be 0, ranging up to 9. So when I actually expand this out, this is called a place value expansion. Writing the 7 is times 10 to the second, 2 times 10 to the first, and 7 times 10 to the 0th. And the same thing will hold for binary. If I have a binary number like 110, I can say that it's valid because all of the digits are either 0 and 1. That's the key thing about the binary number system. And I can interpret it, or convert it to base 10 under the assumption that I'm working with an unsigned binary number by taking each digit and actually weighting it according to a power of 2. So just like in base 10, that digit all the way to the right, it was worth the least. The digit all the way to the right in binary, we're going to call that the least significant bit. And the reason that we're calling it a bit is in the binary number system, each digit can be referred to as a bit. So this least significant bit 0, if it is going to, or rather I would say it has a weight of 2 to the 0th power. As we move one bit to the left, it will have a weight of 2 to the first power. One additional bit to the left will have a weight of 2 to the second power. So this 0 is, of course, worth 0 because the digit is 0. This 1 is worth 1 times 2 to the first, or 2. And this one is worth 1 times 2 to the second, or 4. So this is the ones place, the twos place, the fours place. And if we kept going to the left, we'd have the eighths place, the 16s place, the 32s place, and so on. And you'll get to see some more of that in the example problems. But just know some terminology that one digit in a binary number is called a bit. If you have a group of 4 digits or 4 bits, it's called a nibble. And a group of 8 bits is called a byte. And of course, in the majority of modern computing devices that you see now, whether you're talking about the actual bus width for a microprocessor, or the amount of information that can be stored in some type of long-term storage device like a USB or an external hard drive, you see the word byte a lot more than bit, because in order to have storage capacity, or in order to have information flow or bandwidth capacity, you need a lot of bits. So how are these actual binary encodings manipulated? Well, they're going to be manipulated using the concepts of Boolean algebra. We're actually going to combine them using this idea of logic. And the hardware that actually composes a modern digital computer is actually implemented at this level, at what is known as the actual gate level. So I put a sheet that I want everyone to make sure that you're aware of, and we'll look at a little more in some details in the example problems. But there's a logic gate cheat sheet that's on your Canvas module now. And if you'll notice here, these individual symbols that we're seeing, these are referred to as schematic symbols. And a schematic symbol is just kind of a graphical representation. It doesn't actually imply how the underlying hardware works of a gate or a piece of hardware that's capable of implementing these actual digital operations that we see. So for each of the gates that I'd like you to be familiar with, and you're going to get some experience working with, you'll want to remember the symbol, the actual name, along with the Boolean algebra representation, things like multiply. Notice that multiply corresponds to an AND operation. Add corresponds to an OR operation. We also have this inversion operation, which we denote by taking an input variable and writing a line over top of it. And in addition, since these are functions here, they are Boolean functions, we need to know the relationship between the output and the input. And since these inputs are Boolean variables, they can only take on a 0 or 1, the total possible combinations of inputs is pretty small. So we can, rather than like if you think about traditional functions where you might have to draw a graph in order to show the relationship between all the possible inputs and all the possible outputs, in actual digital or Boolean analysis, we can list all the possibilities in a table. And these are what are known as truth tables. So Key point that I want you to realize here is inside the computer, whether it's actually doing mathematics or doing computation, that operation is known as building what is called combinational logic circuits. We'll see a little bit of that in the example problem. Or whether it's actually implementing circuits that have the capability to store things, which those types of circuits are called sequential circuits, and they're performed through feedback. All of the things that are done inside a computer are done at this gate level. And inside the gate, it actually consists of transistors, which are a more complex component that you don't need to know for this course. But computer engineers, when they actually build the hardware that does all the things we're going to talk about in this course, they're designing at the actual gate level. And in terms of some key ideas that you might want to be familiar with when you're going to tell someone that you're an engineer and you're familiar with how to not only to code computers but how the underlying hardware works. The big kind of breakthrough in this came when we realized, coming from a mathematical point of view, in the late 1800s, that any actual Boolean operation can be accomplished through either using exclusively NAND operations or exclusively NOR operations. And for those of you that are familiar with linear algebra, that's to say that those functions form a basis over the set of all Boolean functions. So from a hardware point of view, what that means is if you can build a NAND gate, you can do anything you want to do. And in modern integrated circuits, that's the way that they're typically laid out, using only actual NAND type operations. Another thing that's important to know is actually, as the actual form that we've used to implement hardware has changed over the years, it's gotten smaller and smaller and smaller under this kind of prediction that was made by Moore. I'm sure many of you saw over the weekend that Moore actually passed away in his 90s. Very sad to see, and very ironic that we're going to be talking about him today, and he actually died over the weekend. But the idea that however you physically build these, as long as they're capable of implementing this type of logical behavior, that's an idea known as abstraction. So the actual hardware of the computer can change, but as long as you can implement these gates, you can still implement the underlying function. So just a little bit, I don't want to go into a lot of detail on this because I know many of you have seen this beforehand in the intro course, but do feel free to kind of dive into it a little bit more, look at some of these links and read it. The key thing that I want you to realize here is the underlying ideas of what the computer that you're working with right now date all the way back to the early 1800s. People were actually able to design and understand how these things would work long before they had the capability to actually build them. And that's an important thing to know because from an engineering point of view, we often think that, if you're not working in a lab, you're not doing engineering. But oftentimes our capability to do analysis and design things before we actually have the hardware available, that's a very common thing that happens. Even if you look at what's going on in artificial intelligence now, if you look at a guy named Geoffrey Hinton, the idea of the actual deep neural network, he had it decades ago. So why are we actually only able to build it now? Well, we have advancements in data sets, we have advancements in algorithms, we have advancements in GPU hardware. So it's very common for design kind of on paper to precede the capability to implement something in practice. So the early kind of implementations of the digital computer, Charles Babbage was a big godfather of that, and he actually considered himself an engineer. So important to know that it's not computer scientists that were developing these things. It is actually people that considered themselves engineers trying to do mathematical problems. The first actual machine that was put together that had those three components of processor, memory, and I/O was this machine, rather, I should say, was actually Turing complete. That's an idea of a godfather of computing known as Alan Turing, a very cool story to learn about, particularly his contributions during World War II and just a lot of the oppression that he faced just based upon his background. It's a good thing to look into and realize why all of the efforts that we have to make computing more inclusive are so important. In addition, the first actual program developed on this analytical machine, as it was called, as we see down here in the lower right, was actually developed by Ada Lovelace, one of the just phenomenal contributors in computing and first females contributing in computing. And if you're familiar with NVIDIA's new hardware line, the GPUs are actually called the Lovelace GPUs. Now, even though these ideas were around in the early 1800s, the first fabrication of an analytical machine didn't happen until 1941. It was done for problems in computational fluid dynamics, pretty similar to the idea of using computing to solve problems in science, as we spoke of beforehand. But the key point I want you to realize is everything that you're working right now, those ideas of modern computing are very mature. People have had them for hundreds of years. But the thing that's made them feasible in scale for everyone to have one at a cheap price point is actually advancements in engineering, particularly like material science and semiconductor science. And we'll look at that a little bit here. So you can read over all this if you want. Just to keep the video short, I'm not going into a lot of details here. But the key point to realize is that not too long ago, right, here's a picture of a computer in 1949. And it actually operated using using the same principles that the computer you're using now did. It's just that its form factor was tremendously different. And the reason that we were able to really shrink that form factor is the actual implementation of integrated circuits. And under the hood, an integrated circuit is nothing more than a collection of a bunch of transistors. And here you see the electrical schematic of a transistor. And without going into a lot of details, basically it works a lot like the actual light switch that you probably have turned on and off quite a bit of times today. You actually place a signal at the gate, and that signal at the gate controls the connectivity between the source and the drain. So you can just basically look at it as a simple digital switch. But those were invented in 1947. The first integrated circuit was developed in the 60s. And as we learned to put more and more of these on a chip, remember that under the hood, they're what actually enable these gates to work. We were able to make the personal computer feasible. And if you just look at how quickly this has came into actual practice, in 1983, the year that I was born, there were 5 million worldwide PC sales and 340 million in 2021. And as we spoke of earlier, personal computers are only a subset of the actual computing devices that we have at our disposal now. And here is Moore's Law. It kind of feels weird to talk about it, given what happened over the weekend, but this is plotted. If you notice, the y-axis here is logarithmic. Basically, the rule of thumb you want to remember when you're working in computing is that every 2 years up until now, the number of transistors that we can integrate on a fixed piece of silicon is doubled. And that has made things cheaper. It's made things more computationally powerful and really led the computing engineering revolution that we have. So what I want you to take away from this, when you think about computing, think about it as the process of doing math. Know that it's by engineers and for engineers. The ideals are old, and what's made kind of the modern feasibility that we have is advancements in integrated circuits, which are processing discrete information, particularly binary. And we'll get a chance to look at a lot of these ideas in the actual example problem module in the next video.